In this video, I'm going to talk about the Bravais lattices and the allowed crystal symmetries. And so this is looking at the group symmetries essentially of the lattice itself. So an empty lattice and what sort of symmetry the lattice itself has. And from there, we will sort of start, well, in the next video, I'll start sort of, thinking about inserting objects with symmetry into the lattices and how that affects the symmetry of the lattice itself. And so this, we're kind of looking at the symmetry of an empty lattice. And so first we have, if we have these primitive translations of the A1, A2, A3, so we have this as a basis, and then the components is the T1, T2, T3, and we map our operation, either a rotation or reflection or something, onto this matrix R, and we do it in this basis. And so I've talked about in a previous video how when we do the mapping, it has to be in a specific basis. And so that's always kind of important to remember, is that a mapping depends on the basis. If you're in a different basis, then the mapping is going to be different. And so we're mapping in a particular basis here. So we're doing this mapping of our symmetry operation to this matrix. Then we want to rotate a translation. So we have this translation from T to T prime, and we want to rotate that. The translation T must have integer components, and so does T prime, and therefore the elements of R must also be integer elements. And in fact, the trace here of the matrix has to be integer elements. And so in order for that to be the case, then cosine of theta has to be equal to either 0 plus or minus 2, because that would cancel out the 2 there, plus or minus 1, plus or minus 3 over 2, which would also cancel out the 2, plus or minus 2, so on and so forth. And this means that we can only have angles theta which are equal to some integer times 2 pi over some integer n, where the integer n is the axis of rotation, or the order of the axis here. And so what we find is that n can only be equal to 1, 2, 3, 4, or 6. And the reason for that is because we see if we have n equals 1, then this equals 1. If we have n equals 2, this equals negative 1. If we have n equals 3 and k equals 3, then this equals 1. If we have n equals 4, it equals 0. And if we have n equals 6 and k equals 3, then we have minus 1. And so for 1, 2, 3, 4, and 6, we get these integers for the cosine here, which is what we said we needed up here. But if we have n equals 5, then no matter what k we put in here, 2, 3, 4 here, we end up with these non-integers here. And so the n equals 5 will not actually be able to be in our crystal lattice. So those can be a point symmetry, but they can't be a lattice symmetry. Because they don't give those integer traces. So there are only 27 axial groups satisfying the requirement, and only 5 cubic, which are the tetrahedral and octahedral groups, bringing it to 32 acceptable point groups. All right, so if you look at our crystal systems, different lattice types are distinguished by the relative lengths and mutual inclinations of the vectors. And so, we're thinking about the vectors. So in 2 dimensions, we have our 2 vectors like this, but they also might be at some obtuse angle or some acute angle. We might have one that's longer than the other. And so the different lattice types are distinguished by the angles that these have with each other and the relative lengths that they have with each other. This means that they are characterized by their metric. And so remember, the metric, it can be shown as a matrix where each element is sort of a dot product of the different bases. And so the scalar product of 2 lattice vectors, so we have these 2 lattice vectors R and S, so the scalar product is defined by G, so we can put that in there, and it has to be equal to some scalar quantity here that's a real number. And this must be preserved after a rotation by r. So we get the r tilde and the s tilde here. So the r tilde dot s tilde here must also be equal to this constant here, this scalar, which is a real number. And so it must be the case that if we take the conjugate of our metric here, that we just end up with our metric again. And so the metric is the same under all these transformations, which is sort of a long-winded way of saying that we have to preserve lengths and angles after a rotation or reflection or whatever the symmetry operation is. So in 2D, the point group C2V has two generators, the C2 and sigma V, and they have these properties where if we do it twice with either the rotation or the reflection, we get the identity element, and these ones are actually commutative. And so the matrices with integer elements that possess these properties are these. And so we have this -1 on the diagonal for our rotation, which makes sense because if we have, some vector here and we rotate it 180 degrees around this point, it'll be pointing in the exact opposite direction. And then the reflection, we have this and this. Well, it can be this or this. And so this first one here would be something like if we have a vector like this and, we have the coordinates like that, then we reflect it, and its sort of component here would become negative, and we would end up with that. Then this one with the off diagonals would also sort of change the way that, it would change the x component into the y component and the y component into the x component is what that is doing. And so those are the reflections, or the matrices we can use for reflections. And so what we require is that the metric, if we're using this ones in the off diagonals here, is that the metric here in blue, which is just the where the metric with the components or elements in the usual place, is the same even if we sort of switched the diagonal elements with each other. So kind of like that, and the off diagonal elements with each other to get this red one here. And so we can see that this, if this is true, then if we take the conjugate of this red one here, which is what I'm doing in all of this right here, then we get this blue one. And so I actually went through the matrix multiplication, which you can sort of look through on your own. If you want to look at the lecture notes, they will be linked to in the description. And so you do the matrix multiplication and you do indeed get this blue one. So it's because we have said that the requirement is that if we take the sort of sigma v of our metric and then the sigma v inverse of our metric there, which because it's 2D, our sigma v inverse was just equal to the sigma v, which is why we're using the same matrix in both places. But we said the requirement was that this was just equal to our metric. And so if this is true here, then the blue and the red have to be equal to each other. And so we have to have sort of the A1 and A2 be equal to each other. And so this describes a basis that are equal in length but have arbitrary inclination. And so then if we do the same thing for this 1 minus 1 in the diagonals, so we have this one here, and then it has to be equal to this one where these two off diagonal ones turn into negatives, and so we do the conjugation, and so you go through all the matrix multiplication, and indeed you find that that is the case, that this blue one is equal to the red one through conjugation, which has the basis vectors that differ in length but have an inclination of theta equals pi over 2, which is 90 degrees if you want to think about it in degrees. And so these are the 5 2D Bravais lattices. And so we see here we can look here on the first one, this oblique one. We have that the two basis vectors don't have to be equal and the angles don't have to be 90 degrees. We have the rectangular one where the two basis vectors don't have to be equal, but the angle between them has to be 90 degrees. And so that's kind of what we had up here. So the basis vectors can differ in length, but they have to have this 90-degree inclination. So they have to be 90 degrees from each other. And then we have the centered rectangular here, and we have the hexagonal, which is this where we have the bases equal to each other and the angle is 120 degrees. And that's similar to what we had up here where these are equal in length. And this is arbitrary inclination, but this hexagonal one is specifically 120 degrees. Sometimes you will see this written where if you have this basis right there, then they go to that one rather than going to that one right there. But you know, this would just be a 60 degrees right there. And then we have the square one, which is that the bases are equal to each other and the angle is 90 degrees. So that's the 2D Bravais lattices, but we will be interested in the three-dimensional ones here in a minute. So the set of all operations, so all our symmetry operations, so the R, which can be rotations and reflections and things like that, that by reflection or rotation with the origin bring the lattice into self-coincidence, is the point group of the lattice, and that is called the holohedry. And combining our group of operations with translations gives us isomorphic point groups at every lattice point. And so that's essentially saying if we have our lattice here, so say we have a lattice that looks like this, and a perfect lattice would be one that sort of extends off to infinity in every direction. So it would be something that looks like this. So what this is saying is that if we have some symmetry at this point here, if we then translate to this point here, you know, and this would be sort of extending off to infinity here, the symmetry would be the same at this point as it is at this point. So every translation brings us to another point where the symmetry is isomorphic to the, I guess, origin point. So distinct lattices can have the same holohedry G, and these lattices with the same holohedry are the crystal system and are known as the syngony. And so these words kind of look a little strange, these holohedry and syngony, but if you just kind of break them down into their roots, so this H-O-L-O, hollow, so if you've ever taken like you know, like a biochemistry class, you might have heard of like the hollow protein or the hollow enzyme, which is like the complete enzyme or protein. And so hollow is telling us that we have sort of the full thing. And in fact, in the next video, we will run into the hemihedral, which is sort of partial of the holohedral, but I won't get into that now. And then syngony, so S-Y-N, sort of the same thing as like synergy, so, you know, working together, or synthesis, bringing things together. And then this G-O-N here is the same as in polygon, and so it's sort of saying same polygons, you know, which makes sense because we're talking about these polygons that look kind of like this. They have these squares and hexagons and things like that. But in other words, the lattices, Mi, with the holohedry G, form a syngony, which I wrote here as S sub G. So S sub G is the syngony, and it is the set of all the lattices M sub I there. The 7 allowed metrics for a 3D lattice are described in this following table. And so here we have this metric here, which we see in the description. The A1, A2, A3 are unequal and have arbitrary angles, and so the the elements of this metric here can sort of take on any value here, and so that gives us the triclinic here. Then the basis for the monoclinic here, A1, A2, A3 are unequal in length, but with the A1 and A2 perpendicular to the third A3. And so to show that they are unequal in length, we have M here, and then M prime, then M double prime in the lower corner there. And so the diagonals on the matrix tell us about the length of these bases, and then the off diagonals tell us about the angles. And so because the first two have to be perpendicular to the third, we have these small m's in these two off diagonals here. Then the orthorhombic, so the A1, A2, A3 are unequal in length and they're mutually orthogonal. So we have M, M prime, and M double prime, and then all the off diagonals are 0. And so the bases are different lengths, and the zeros in the off diagonals tell us that they're mutually orthogonal. They are independent of each other. That's kind of what those zeros in the off diagonals mean, is that they're sort of independent of each other. Then we have the trigonal or rhombohedral, which the bases A1, A2, A3 equal in length and equally inclined. And so we have the capital M's in the diagonals here without any primes because they're all equal. And then these M's in the off diagonals because they are equally inclined from each other. Then the hexagonal, the basis A1, A2, A3 equal in length and inclined at 120 degrees and in plane perpendicular to A3. So we see that A2 and A3 are equal in length, and then A1 and A2 are equal in length, and A3 has the prime, so that is not equal in length. And then these minus m over 2's in these off diagonals here are telling us that we have these 120 degrees in plane perpendicular to A3. And then the tetragonal, we have the A1, A2 equal in length, A3 different, but they're mutually orthogonal. So this M and this M are the same, and this M double prime down here is different in length, and the off diagonal zeros tell us that this is mutually orthogonal. And the cubic, I think you can guess, the diagonal ones are all the same, and then everything else is 0 in the off diagonals because they have to be equal in length and mutually perpendicular. And so what we see here in this right column, these are actually the holohedry of these names here are actually the names of the syngonies. And so a syngony has a holohedry, and that's what's in red on these things. The ones in black, as we will explore in the next video, are the hemihedries of these syngonies, but the red ones are the holohedries. And like I said, in the next video we'll find out that the holohedry is sort of the full symmetry. So if you put an object with this D3D symmetry into a trigonal or a rhombohedral lattice, then the resulting crystal made out of those objects, those molecules or whatever, will that whole lattice of them will be D3D. But if you put something into this trigonal rhombohedral lattice that has lower symmetry, then you start having to remove symmetry elements from D3D, and you'll go down to D3 or C3V or something like that. And so, like I said, I'll talk about that more in the next video. So we can actually look at the pictures here of the different syngonies. So these names here are the syngony names, and so we can see this one, the A, B, and C are all not equal. All the angles, alpha, beta, gamma, are not equal to 90 degrees. That's what we had up here for our triclinic. The monoclinic, so A, B, and C not equal. Beta is not 90 degrees, but alpha and gamma are 90 degrees. Then, of course, we see these P and C here. So these are just telling us different things about the crystal lattice, about sort of the way that objects in it can be sort of oriented. I'm not going to get too much into that right now. For now, we'll just look at So we'll go on to the orthorhombic here. So A, B, and C not equal, but alpha, beta, gamma are all equal to 90 degrees. And that is true whether we have the P, the I, the C, or the F. Then we have the tetragonal. So A and B are equal, but C is not. Alpha, beta, gamma equal to 90. We have our hexagonal here, which is the A equals B, but not equal to C. So these are sort of isosceles triangles going around here. Then the alpha and beta here are equal to 90 degrees, but the gamma is equal to 120 degrees. Then this trigonal R here is what we have up here for the trigonal rhombohedral up here. And so we see we have this sort of shape sort of inscribed in this this object here, in this sort of hexagonal looking object up here. Then of course we have the cubic, so A equals B equals C, alpha equals beta equals gamma equals 90. And so those are the types of these are the synganies, I guess, of the Bravais lattices. And so so I actually had this other table over here, and it just shows the same thing, but I just wanted to show that you'll often see these written with these point group names. So these are the Hermann-Mauguin notation names. And if you've ever done X-ray crystallography, which I have, you have probably seen these kind of names, all the M's and N's and things like that. And so you know, this shows it for all the different point groups, and then all the different sort of primitive, base-centered, body-centered, and face-centered here. But as we will discover in the next video, there are actually a lot more than this, because there is the screw axes and the glide planes and things like that that sort of add a lot more different types of crystals that we can have. But I'm not going to get too much into that right now. So right now we will go down here, and so this is looking at the holohedry of the Bravais lattices. And so the Bravais lattices are the ones that are, you know, simple triclinic or simple monoclinic or base-centered monoclinic. Those are the names of the Bravais lattices. And so the Bravais lattices are the point groups of a lattice. And so, like I said, we are looking at an empty lattice. So we're looking at a lattice that doesn't have sort of any molecules or anything like that put into it. And we are just looking at the point symmetry of the lattice. And so if we have some lattice that, you know, looks like this, like I said, extending off to infinity in every direction. What we're saying is that, you know, if we have like this square lattice, then you can rotate the entire lattice 90 degrees, the entire infinite lattice, and it will then become superimposed on itself. Like I said, in the next video, we'll start thinking about what happens if we sort of start putting things with symmetry into each of the lattice points and what that does, and that will bring us to that idea of the hemihedry of these lattices, because we're sort of reducing the symmetry of the lattice itself by putting objects in it that have less symmetry than the lattice. But like I said, I will get into that in the next video. And this one, so I hope you got this idea of what a Bravais lattice is, and there are these sort of 7 different synganies here, but then they can be broken down into these face-centered, base-centered, body-centered, and simple. And so each of the different synganies have sort of a different number of those extra sort of symmetries put onto it, or extra, I guess it's not symmetry. Well, it's symmetries. But anyway, if you add up all these things, we have 1, 2, 3, and then 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there are 14 distinct Bravais lattices belonging to the 7 synganies. And that is kind of the take-home message from this video. And I guess the other one, which will be important in the next video, is that the the lattice within this syngony has these point group symmetries. That's the actual point group symmetry of the lattice. A Bravais lattice is the point group symmetry of a lattice, of an empty lattice, essentially. And then, so like I said, in the next video, we will be looking at what happens when we put objects with different symmetries into a lattice with this symmetry. You know, for instance, putting something with lower than D4H into a D4H, and we have to get the hemihedral. But anyway, I'm kind of rambling. I hope you found this video helpful, and I will see you in the next one.